we're talking about frequently misunderstood foundation design provisions. So the general overview here, we're going to spend the first section talking about load combinations for foundation design. We'll get into details on service level design, ultimate level design, seismic considerations, and also some thoughts on hydrostatic loading and how that weighs in for evaluation of water table. Then we'll have a 5-minute break, and then we'll have a question and answer. Then we'll go into some discussion on mat, foundation, and spread footing design and detailing. Then after that, we will have our second break, and then we'll follow up with question and answer, and then we'll close out with discussions on deep foundation detailing and some basic discussions of soil structure interaction, and then some high-level discussion about how to apply soil structure interaction to your projects. So with that, we'll get started on load combinations. So the most frequent misunderstandings that we see in load combinations in the foundation world is just incorrect understanding of how they are applied to foundations. There's numerous exceptions and special conditions that you need to consider that are unique to foundations. There's also some confusion since there's actually two options for allowable stress design load combinations in IBC, and most people aren't clear on when to use which of these. There's also frequent misunderstanding about factors associated with seismic effects and how those are applied to foundations. And then finally, we'll close out the discussion with evaluation of groundwater elevation and hydrostatic pressure, because simple code application of code without thinking about it too much will lead to a very overly conservative treatment of these conditions, depending on your project. So typically in the foundation world, we will use both allowable stress design and load resistance factor design or ultimate strength design for design of the foundation elements. And some examples for when you might use allowable stress design is when you're sizing the soil foundation interface, for example, checking bearing pressure, or communication of loads with a geotechnical engineer. And generally, if there are working in service level loads. Whereas a load resistance factor design or ultimate strength design is used for typically designing concrete elements. For example, design a flexural reinforcement, design a shear reinforcement, and checking punching shear. And this is just a reaction to ACI 318, is of course all based in LRFD, ultimate strength design. So when we talk about those load combinations, these are the load combinations as referenced by the IBC. So the strength design, most everyone knows those, you learn those in school. The allowable stress design is where it gets a little confusing. There's two sets. There's the basic allowable stress design, and there's the alternative basic allowable stress design. The basic, you'll note, there's a, I'll use my pointer here to clarify. The wind and seismic overturning cases have a 0.6 dead factor on the basic. On the alternative basic, the load factor on dead load is a little bit different, and there's some other nuances in what dead load can be used to resist wind and seismic in the alternative basic. So in general, if you compare the LRFD and the basic allowable stress design load combinations, which are taken directly from ASCE 7, these are relatively consistent regarding overturning factor of safety. The 0.6 dead factor on ASD, that was added in ASCE 798 to address the inconsistency in the treatment of counteracting loads when comparing allowable stress versus strength design, and it also just emphasizes the importance of stability in foundations. The alternative basic is actually from UBC 97 and before, and these, while they're still included in the IBC, they're considered legacy load combinations, and it's kind of a reaction to lobbying at the ICC level that some West Coast engineers did not want to take that overturning factor of safety increase. And someday we do expect that these will be eliminated from the building code, but for now they're available as an option to use. So a few more notes on the alternative basic ASD is that when dead load is counteracting wind load, only 2/3 of that dead load likely to be in place can be used to resist overturning, which effectively forces a factor of safety of 1.5. Therefore, for wind compared to basic ASD, it's relatively similar. It's not so similar for seismic. So the question is, therefore, which should you use? The alternative basic ASD will result in a lower factor of safety for seismic overturning, and it won't be consistent with LRFD. That's the fundamental problem, that if you are doing an analysis at alternative basic ASD and then scale up to LRFD for design of your concrete elements, you could actually get something that becomes unstable on the LRFD load case. So therefore, the basic ASD will be more consistent with the LRFD evaluation, and that should avoid a potential analysis stability issue. A couple more notes regarding load combinations for seismic. These are things that are commonly missed or not applied to foundations, but specifically you're allowed to reduce your foundation overturning or seismic by 10% for modal analysis and 25% for ELF. This is just in recognition that these methods are overestimating your foundation overturning. These can be applied to the basic ASD and LRFD load combinations, but they cannot be applied to the alternative basic ASD load combinations, which further kind of muddies the water when you're comparing the load combination options. Another important consideration is vertical seismic load effects, and specifically where you do and do not need to include this for evaluation of foundations.